In this video, we're going to do some counting examples. I called it Advanced Counting Part 1 because it's a mixture of all different types of counting where we may or may not need the addition principle and or the complement rule. Likely we will still be using all the other tools, so the multiplication principle, the permutations, and the combinations. So let's get started. Suppose we have a set S that contains the elements A, B, C, D, E. So this means that the number of things in S is 5, so there's 5 elements. How many different 2-element subsets are there? So remember, a subset of S is any set that uses only the letters A, B, C, D, E, so the ones that are in the set S. And we want these ones to have 2 elements in particular. So we need to select 2 elements from the set of 5 elements in S, and because we're putting them in a set, the order we write them doesn't matter. So we're going to use a combination. So there's going to be 5 choose 2 or 10 different 2-element subsets of S. Now, what if we wanted to know how many different subsets of S are there in total? So one thing you might do is to break the problem up by how many elements there are. So then we use addition. So we would add the number with 0 elements plus the number with 1 element plus the number with 2 elements. And we have to go all the way up to 5 elements because we could in fact take them all. And each of these are fairly easy to compute. So for the first one, I want to pick none. So if you want, you could do 5 choose 0. But in fact, the only one here is the empty set. So 5 choose 0 is actually just 1. So that's a 1. If we want 1 element, we just have to pick 1 element from the set. We already did 2 elements. So we know that one's 5 choose 2. 3-element subsets, we pick 3 of the 5 elements. For 4-element subsets, we're going to pick 4 of the 5 elements. And for the last one, we pick all of the 5 elements, and 5 choose 5 is also a 1. So we end up getting 1 plus 5 plus 10 plus 10 plus 5 plus 1, which happens to be 32 in total. Okay, so this is using the addition principle because the different subsets either have 0 elements, or they have 1 element, or they have 2 elements, etc., etc., and they can't happen at the same time. So you don't have a set that has both 2 and 3 elements. Okay, they're different numbers of elements. Another way that you could think about this is using the multiplication principle. So we're going to have 5 different steps, 1 for each element of S. Okay, and then the number of options. So what we're going to do, remember, we can break this into a series of decisions. So for A, our decision is, do we put you in the set or do we not put you in the subset? So there's going to be 2 options for each of these elements. So this is 2 to the 5, which is also 32. Same idea. So I'm just going to write here. The 2 options are in or out of the subset. Okay, so in or not. So if you say no, 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 if you say no to all of them, that's an option. That's going to give you the empty set. If you say in for all of them, that's going to give you the full set with 5 elements. If you say in, out, 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 you're going to get the set A, B. Okay, so you can see that you get all different size sets, subsets, with this one strategy. Okay, either works, so you're welcome to use either method. Okay, let's try another one. how many different subsets have at most 2 elements? Okay, so when we say at most 2 elements, that means they have 0, 1, or 2 elements. Okay, so it's easier to count when we know exactly what's happening. So here it's going to be beneficial to break it into cases. So it's going to be the number with 0 elements plus the number with 1 element plus the number with 2 elements. Okay, and we've kind of already done these. So this is 5 choose 0 or 1, 5 choose 1 or 5, and 5 choose 2, which is 10. So we get 1 plus 5 plus 10. So there's 16 of these in total. Now, if they want at least 2 elements, okay, that means you're going to have 2, 3, 4, or 5. So you definitely could do that. So if you count it directly, you're going to have 5 choose 2, plus 5 choose 3, plus 5 choose 4, plus 5 choose 5. So that's 10, plus 10, plus 5, plus 1. So 26, okay? Or we could use the complement here. So remember, remember I said that 3 cases is usually my maximum. So if there's more than 3, which here we have 4, I might think about the complement. So you're going to have the number in the universe minus the number with not at least 2 elements. So that's less than 2 elements. So this is going to be 32, because we already computed the universe, minus the number with 0 elements, plus the number with 1 element. So there's a bit less work involved, but for this one, they're both similar. So no elements, there's 1, the empty set, 1 element, there's 5. So we need to subtract both of those, and again, we get 26. Okay, let's try another one. So this one, the setup is a bit complicated, so let's go through it. So we have a grid below which shows city streets in a city. A group of bank robbers decides to break into a bank located in the top left corner of the grid. And the hideout they're trying to get to is in the bottom right of this grid. Okay, now they're going to take shortest routes, so that means that they're only going to move south, so down, or east, which is to the right. Okay, so those are the only moves they can make. So maybe I'll just write, so south, they're going to go down. Okay, east, they're going to the right. So those are the only ways that they can move. So for part A, we want to know how many different paths are there from the bank to the hideout. So we want to get from here to here. So you could do something like that. Okay, that would be one path. Now this is hard to count. So we might want to try to think about another way we can visualize this problem. Okay, and it turns out that these paths are actually correspond to a string of letters. Okay, so paths from the bank to the hideout correspond to a string of now how many letters? So how many downs do they need to make? 1, 2, 3, 4, 5, 6, 7, 8. So no matter which way they go, they're going to have to go down or south 8 times. And they're going to have to go east or right 7 times. Okay, so that means they have to make 15 moves in total. So our string is going to be 15 letters. So let's just see how these correspond. So let's just make one path here. Okay, so here's a path from the bank to the hideout. Now I wish I could use the same color, but I cannot. So the green, okay, so I'll just write green here. The green path, so it goes right twice, or 3 times, sorry. So I'm going to write that as 3 R's. And then it goes down twice, so 2 D's, and then it goes right once, and then it goes down 3 times, and then right twice, down once, right, and then down, down 2 more times. So let's count. 4, 5, 6, so there's 7 R's. And 8 D's. Okay, now it turns out that every path is going to be a string like that. Now, what if we made a string that has 7 R's and 8 D's? So I'm just going to do another one. So D, 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 R, R, D. So that's 5 D's so far. 4 R's, 6 D's, R, R, R. So I'm done with R's. 1, 2, 3, 4, 5, 6. 2 more D's. Okay, so here's a path. Well, maybe. So let's follow this and see if we get from the bank to the hideout. So it wants us to go down 4 times, right twice, down once, right 2 times, down once, right 3 times, down twice. So notice that we made it from the bank to the hideout. So this is the blue path here. So instead of trying to count paths on this grid, we could try and count strings of this type. Okay, and it turns out that's going to be easier. So let's just write this. So the number of paths equals the number of 15-letter words, let's say, instead of strings. Okay, with 8 D's and 7 R's. Okay, so now we just want to know, how do we count that? So when you're doing this, so you're going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So you're going to have 15 spots. And all we need to know is where are, say, the R's. Okay, so I need to pick 1, 2, 3, 4, 5, 6, 7 places for R's. Okay, and then I'm going to put R's in each of these. Okay, and then the remaining have to be D's. So how many ways can I select 7 of these 15 spots to be R's? So they're all R's, so the order doesn't matter. So we have 15 spots, and we want 7 for the R's, or you could pick 8 for the D's. It's the exact same thing. So we want 7 for the R's, so 7 of the spots. No order, so the order doesn't matter. So this is a combination. So this is going to be 15 choose 7, which happens to be 6,435 different paths. Okay, so that's how we get the number of paths. Now, suppose there's a police blockade set up at point X. Okay, so here is point X. Okay, it's 2 blocks east and 3 blocks south. We want to know how many of the robbers' paths do not pass through this blockade. So the 2 that we've drawn both miss the blockade. Okay, so we want to know how many paths miss the blockade, so they don't go through. So how many are of this type? This is actually really hard to count, because how do you make sure that a path misses X? Because you could go down far enough so that you miss X for sure, or you could go over far enough so that you miss X. But there's lots of ways that you could not immediately go out of your way to miss X and still miss X. So it turns out that counting, so the number of paths that miss X, this number is hard to count. Okay, but it's easier to count the number of paths that go through X. So what we're going to do is we're going to compute this by doing the number in the universe, which we already computed, minus the number of paths through X. So the number that go through it is the opposite. Those are all the paths we don't want. Okay, so this we know is 6,435. Now we want to figure out, okay, how do I count the number of paths through X? Okay, so here would be a path that goes through X, for example. Okay, this yellow path. So what we want to do is break the problem up. So we first want to get from the bank to X. Okay, so this is going to be step 1, and then we want to get from X to the hideout, because the paths have to go the full way. So we want to know how many there are. So even though you would be stopped at the blockade and you wouldn't be able to continue, we're going to pretend like they can so that we can count the paths that would have done that. So we're going to break this up, and it's going to be the number of paths that go from the bank to X times the number that go from X to the hideout. Okay, so now from the bank to X, do it in here. So there's 3 D's and 2 R's. Okay, so I want the number here, is going to be, there's 5 spots, and I want 2 of them for R's. Okay, so this is select 2 of the 5 spots for R's. Now again, you could do all of this for D's, okay, or you could switch them. You get the same answers. Okay, now from X to the hideout, there's 1, 2, 3, 4. There's 5 downs, and in fact 5 R's. So 10 spots, 10 moves we're going to have to make in total. So I'm going to have to multiply by 10 choose 5. So again, we're selecting 5 of the 10 spots for R's, for our paths. So computing this, you're going to get 3,915 paths that miss X. Okay, but here is, we didn't have a lot of cases, well, I mean, we could have, to find the paths that miss X, but there would be so many that it would be so hard to do. You'd end up just drawing every single path. So it turns out that the paths through X are way easier to count. So here's where the complement rule can be especially useful. Okay, let's try another example. So, inside of a fallen tree live 5 ants and 7 beetles. And Pumbaa is going to reach in and grab 3 bugs at random. In how many ways can Pumbaa obtain a selection of 3 bugs with exactly 1 ant? Okay, so we want the number with exactly 1 A. I'm going to call them A. So that means that I'm going to have 1 A and 2 B's in order to get 3 bugs. Okay, so if I have exactly 1 ant, it means I have 1 ant, 2 beetles. So in order to count this, I'm just going to have 2 steps. So select 1 ant, select an ant, select 2 beetles. So there's 5 ants to select from, and I want 1 of them. So there's going to be 5 choose 1 ways to do that. And then there's 7 beetles, and I need 2 of them, so that's 7 choose 2. So this is 5 times 21, which is 105. Selections are going to have exactly 1 ant. Okay, now we still want to select 3 bugs, but now we want at least 2 beetles. Okay, so what does that mean? At least 2 beetles, we could have 2 beetles, or we could have 3 beetles. Okay, we can't have more than that because we're only selecting 3 bugs total. So we could do this with cases. So the number with 2 beetles plus the number with 3 beetles, which is the same as saying the number with 2 beetles and 1 ant plus the number with 3 beetles, 0 ants. And in fact, this one is part A. It's the exact same, so we can reuse our answer. So we know that's 105. If we want 3 beetles, then from your 7 beetles, just pick 3. And if you want it to look like the answer above, you could continue to pick from the 5 ants, 0 ants. Okay, this is multiplying by a 1. Okay, so you don't really need it, but if you want it, it makes all the cases look the same. So this is 105 plus 35, which is going to be 140. Okay, part C. How many have at most 2 beetles? Okay, so at most 2 means that they have 0, 1, or 2. So there's 3 cases, but we could also think about the complement. Okay, so the complement of at most 2 is more than 2. More than 2 beetles, which is the same as saying 3 beetles. So there's only 1 case here. So this might actually be better, so faster to use. But if you want to do the 3 cases, go ahead, you just add them. So the number with at most 2 beetles is going to be the number in the universe minus the number with exactly 3 beetles that we actually already computed. So now we need to know the number in the universe. Okay, so for the universe, here we don't care what we get. So there's 5 ants and 7 beetles. That gives us 12 bugs in total. Okay, and we want to select 3. So the universe is just going to be 12 choose 3. And the number of ways we can get 3 beetles was our 7 choose 3. So 12 choose 3 is 220 minus 35, so we get 185. Now, if you use these 3 cases and add them up, you should get the same answer. So that might be useful to do. Make sure that you're on the right track. Okay, one more. So here we want still to select 3 bugs, but we want at least 1 bug of each type. So that means we could have 1 ant, 2 beetles, or 2 ants, 1 beetle. Okay, but we have to have at least 1 of each type. Now, I'm going to do this on the side here. So, could we do 3 spots for an ant, a beetle, and then a 3rd bug? So we might think, okay, there's 5 ants, let's pick 1. And then we'll pick a beetle, so 7 choose 1 ways to do that. And then we take out those 2, so there's 10 bugs left, and we just need 1 more, 10 choose 1. So this would be 350 ways. Now, would that work? I mean, I did it on the side, so you're probably thinking it might not, but why doesn't it? Because it does seem like we're going to get definitely an ant, definitely a beetle, and then something else. That seems fine. The problem here is actually that it overcounts. So you're going to get some selections more than once. Okay, so I'm going to try and give you an example. So let's say we pick ant 1 here, beetle 1 here, and then in this last spot we pick ant 2 because that ant is still there. Okay, so we could do that. But we could also pick ant 2 first because when we first picked, both ants are available. And then we pick beetle 1. And then when we pick our last bug, ant 1 is in the mix. Okay, so we could pick ant 1. So notice that these are the same 3 bugs. Okay, but we selected them in a different way. So that means that we've counted this selection more than once. Okay, so this is how we know we've overcounted. So we don't want to do it that way. It's always easier to count when you know exactly what's happening. Okay, so we want to use cases. And we've actually done some of these cases already. So the cases are 1 ant, 2 beetles, or 2 ants, 1 beetle. Okay, so the number with 1 ant is the one we already did. So this is 5 choose 1 times 7 choose 2. And with 2 ants, we're going to have 5 choose 2 times 7 choose 1. Okay, so let me just put an arrow here. So that's that one, that's that one. We add them together. So this one was 105. This one is 10 times 7, which is 70. So in total, there's 175 selections with at least 1 bug of each type. So that's some practice with